All right, it's 5:30. Let's go and get started. Good evening, everyone. How's everyone doing today? Good to hear. All right, and so just like I mentioned on Tuesday, we are kind of moving into final production for the semester. So Tuesday we went over the final project. So you guys can start working on that. And from here on out, I have kind of a long series of I call them kind of like half lectures, and so probably for every single class session that we have from here until the semester ends, I probably not going to be able to lecture the full time on any given topic. And the purpose of that is to, give you guys some time to, first of all, work on the project in class. The ANSYS software in the lab is, a little bit nicer than the student versions that we have on laptops. The element count is higher. There's a few more features in this license. But also, these times will act as kind of extended office hours too. And so if you wanted to ask questions about the projects, kind of seeing you want me to take a look at kind of what you're doing. If you have any questions about the setup or the boundary conditions, now is the perfect time to ask. And so I'm going to try to leave at least, 30, 45 minutes of every lecture from here on out, just to give you guys that chance. Just because I know my standard office hour times, I plan my standard office hours more for my undergraduates, but I know it's a little bit difficult for you guys to make my standard office hours. And so I wanted to have some extra time in the lectures for you guys to kind of meet with me and have kind of one-on-one time for me to look at it. All right, so for today, the plan is to go over this feature in ANSYS called fatigue life analysis. So this is one of the advanced features that you can use on your final project. And again, I don't think this is going to take the entire lecture. Maybe we'll finish in 30, 40 minutes. And the rest of the time will just be kind of open off. Okay, so this is one of the extra handouts that I have posted online. We are going to use ANSYS today. So I'm going to show you how to use it within ANSYS. But there's nothing you have to turn in from today. This is not a formal activity that you have to turn in. This is kind of just for your guys' information and for you guys to have something to refer to if you wanted to use fatigue life for your final. All right, any questions I can answer before we get started for today? Okay, all right, so let's go over fatigue life analysis. All right, I'll have kind of a short lecture portion, but the majority of the time today will be spent within ANSYS. Okay. Now, fatigue life is quite interesting, and it's you can say it's a little bit different than kind of how we assessed failure, up until this point in the class. All right, so the idea of taking a mechanical part and applying loads to it and seeing if it fails is nothing new to us, and so we've done that in almost every activity so far. But up until this point, we've only really considered one type of mechanical failure within a part, and that's what's called material failure. And the reason it's called material failure is because we are checking for if our stress exceeds the yield strength of. That's essentially how we've been doing it. right? And so if our equivalent stress exceeds the yield strength, then we say that the part is going. Another way that you can kind of describe this is that this is what's called acute failure. So this is failure that occurs kind of right away. And so this is something that if you ever load an object beyond its yield strength, it's just going to fail. Doesn't matter if the part is brand new. Doesn't matter if the part is used for a long time. This is something that is catastrophic. Now, this is not the only way that a part can fail or mechanical structure. Another very common way for structures to fail is through fatigue. If anything, fatigue is probably the more common mode of failure for any reasonably designed engineering structure, right? Usually, if you're a decently skilled engineer, designing a structure, hopefully you're not putting any loads on it that are needed, unless there's a very unexpected amount of load that but most of the time, when you see things failing, when you see bridges failing or things collapsing, it's usually due to fatigue. And what that basically means that, over the course of time, so as a structure, experiences different amounts of loading, we call loading cycles. And so, cycles where the structure is loaded, unloaded, it's loaded, it's unloaded, right? That's going to gradually weaken the material over a long period of time. So the way that we kind of perceive it happening is that the material or the structure gets tired. Right? So just like the same as humans, after we do things repeatedly for a long period of time, we stress ourselves. We get fatigued, we get tired, right? And so we can't handle things like we could when we're full of. And so when a material gets fatigued, right, its threshold for failure kind of goes down. And so a smaller amount of load or a smaller magnitude that normally would not cause failure if this part or structure were brand new, under fatigue could cause failure of the structure. Okay. So obviously, if you're going to be designing a structure or a part, fatigue is something that you're likely going to be very interested in because you want to make sure that your structure is not only going to be structurally sound when it's brand new, but is going to be able to survive the many loading cycles or be reliable over a long period. Right? And if you're going to be going through the trouble of running a finite element simulation and computing things like the deformations and the stress, then a lot of times you're going to be interested in its fatigue life analysis as well. Just so that you have an idea of what the lifespan of your part is going to be, whether it's serviced at any given time, lengthened at a given time, right? These are things that you likely want to know about whatever structure you're using. All right, so there's a lot of motivations to solving for fatigue life analysis. Okay? There's one big problem of doing so with FEA. Okay? Now, when you run a computational simulation, and this is true for any computational tool, it's true for CFD, finite volume, finite difference, finite elements, right? Any computational tool excels at solving for things in the short term, right? So for the result after a couple of seconds, at most maybe like a minute of time. So the main issue with fatigue life analysis is that FEA can only solve So FEA is great if you want to find out the instantaneous stress in an object, even when there's dynamic motion involved, right? So even if you have a car crash, right? FEA can compute the instantaneous stress and it can give you that. Okay. Fatigue is a very interesting phenomenon, and I would make the argument that it's not something that we have full full understanding or full grasp of exactly what's happening to material as it fatigues, because it happens over a very long period of time. And likely what's happening is that there's changes that are occurring, at the molecular level within the material that as it undergoes these, cyclic loading cycles, many loading cycles, and we're talking thousands, hundreds of thousands, millions of different loading cycles, right? There's probably a lot of, micro fractures, micro damage to the molecular structure of material. That's really kind of impossible to simulate in FEA. And so how do we kind of merge these two ideas? And so how do we take a tool that's really only designed for short-term analysis, and how do we use that to predict something that's going to occur over a long period? Right? Even just neglecting the fact that we don't have great computational models or equations that describe micro damage or microstructure of material. Simulating a million different load cycles on a material, that's going to be extremely taxing on your computer. Even just simulating just 10 load cycles on a material can be taxing on a computer as well. I'll give you another example. It's not exactly the same as fatigue life, but kind of in my own research, a big area of interest right now is something called growth and remodeling, which is the changes that your body undergoes as it responds to like a sickness or responds to damage within the body itself. So think what happens, when you get a paper cut, right? So your body will go and heal that paper cut, but it doesn't happen instantaneously. So it happens over the course of a couple of days. And we're really struggling right now to come up with ways to simulate this process. Just because we don't have tools that can simulate that. So fatigue is kind of the same way, and so there's not that many great tools. So what we rely upon is, FEA will basically rely upon a lot of experimental data that we have on certain materials. So even if we don't have a great grasp on the exact physical mechanism that causes fatigue, there is a lot of data that's out there that scientists have discovered that steel can take this many load cycles before it starts to break down. Aluminum can take this many load cycles before it starts. And so a lot of this data is published in the literature and often, loaded directly into our software. Right, and so once we load this material data into ANSYS, then what we can do is we can approximate, fatigue life behavior for certain materials, based on the loading that we apply, and it cross-references with this experiment. Right? So the important thing I want you to know is that when you see fatigue life analysis, when you see the tools within ANSYS, we're not actually simulating this part for a million load cycles, even though that's kind of what the software will tell you. We're solving for an approximation of what would happen if we were to simulate this for a million. That's an important caveat, and it's a caveat, that we've been working with throughout the entire class. That FEA is only an approximation, but this is an approximation of an approximation. So there's kind of an additional layer here, and so that doesn't mean that this information is not useful. On the contrary, being able to do fatigue life analysis in FEA is incredibly useful, right? It may not be useful for the exact values, and so ANSYS may tell you that this part will last for exactly 57,346 cycles. It's probably not going to be that exact, but at least will give you a sense of the rough ballpark of the amount of load cycles that your part can take before it starts. And so as with anything with FEA, take it with a grain of salt, and just make sure you know how to use it. Appropriately without claiming something to be more. All right, any questions on this so far? Okay, all right, so what is this experimental data that we need? And I will say that not every material within ANSYS has this data. So the main data that we're going to use in ANSYS is something called an SN curve. So an SN curve is a property of a material that you can load in. And this basically tells you the maximum amount of stress that the material can withstand for a given number of loading cycles. So the S in the SN curve stands for stress, and N is number of cycles. And what you're going to see for that, for every material, this graph is going to be a decreasing graph, right? So as you load the cycle, as you load this material more and more, you expose it to more and more loading cycles, the maximum amount of stress that it can withstand gets lower and lower because of the accumulation of fatigue, all that might. Okay, so the curve looks something like this, and so we'll be using structural steel. Structural steel is the default material in ANSYS. It has kind of the best material definition, has the most features. Okay. So your SN curve is going to look something like this. So as the number of cycles increases, and so you expose your part to more and more load cycles, the maximum stress that it can withstand. Okay, so some materials in ANSYS will have the SN curve already loaded in, and so if you use a material that's within the material library, likely it will have an SN curve. So for example, structural steel, which is the one we're going to use today, SN curve defined. I think aluminum alloy is another one that already has the SN curve defined. Okay. Now, if you're going to be inputting a new material, this is something that you have to manually put in yourself. Okay. And so, you're going to have to find that data yourself, for a given. And it's not the easiest properties to find. So, oftentimes, if you are going to put it in manually, probably for a situation where you work for a company and they have that data on hand, because they've already done material testing themselves. Or if you just happen to be able to find like a paper from Google Scholar on your material, then you can put it in yourself. Okay, so but just try to be aware of it. So I would say if you're using a fairly common material, maybe ANSYS doesn't have your exact, the exact, alloy of aluminum that you're using. But if it's close enough, I would say just use it there, just because these numbers are already pretty much verified and validated. But if not, you're stuck kind of putting these in yourself. Okay. So that's the main thing that you have to add to make sure. Otherwise, the fatigue tool is not going to be available. Okay. And so once we get into ANSYS, the main tool that we're going to use to perform this analysis is called the fatigue. So the fatigue tool is something that you can access straight from mechanical. And so there's nothing really special that you have to do. So if you think back to ANSYS Activity 6, there was a lot of kind of extra stuff that had to do with setup and optimization. Thankfully, the fatigue tool is something that's relatively built into ANSYS itself, at least mechanical. So there's not too much that you have to do besides. The main thing you have to make sure is just you have to make sure that your material can actually support fatigue analysis. Okay, so I think that's enough yapping, and so I think next we'll open up ANSYS and we'll actually see how this is done. Okay. So I'm going to do this on just a very simple part. So I think the geometry that I'm going to use is the bike crank from activity 2. Okay. If you're following the handout, you'll see that I use a different geometry. I use kind of activity one. But I don't want to create another cat file, so I'm just going to download the bike crank again and then use that for analysis today. It'll just get the job done. It'll say the same. Any questions on this before we jump into ANSYS? Okay, all right, so let's go ahead and jump to the software. Let me go ahead and share my screen. I'm just realizing I should have opened up Workbench before I put this beautiful penguin. I like penguins a lot. Whenever I go to an aquarium with my wife, I get to really see it. Okay. I do like puffins too. Puffins are also very cute. I just like I like a lot of sea creatures in them. My wife and I, we took our honeymoon to Japan last year and we went to the Osaka aquarium. We had a great time. I also bought probably one too many plushies at that aquarium. Okay, all right. So after you open up Workbench, let's open up static structural, just like we usually do. Okay, and let's import a geometry. So you can import any geometry for this. Again, this is not something you guys are turning in, but I'm going to just load in the bike crank geometry from activity 2, which should still be. Yes, so it should be crank assembly. We'll do the most. Okay. So that bike crank is going to allow us to do our fatigue analysis. But before we jump into ANSYS mechanical, let's check the material properties just so that you can see the SN curve that I was talking about before. Okay. Okay, so let's double click on engineering data here. Okay. Okay. And so right now, the only material that we have loaded is structural steel. Okay, and you'll see that structural steel has quite a few properties that are defined. Okay, so the one that we want to look at here is the SN curve. The SN curve, once it is defined for a material, will allow us to do the fatigue life analysis. Let's go ahead and click on this. Okay. And so if you click on the SN curve here, you can see the curve that was mentioned to you before. Okay. And so just like before on the horizontal axis here, we have the number of cycles. Just be aware here that this is expressed as log base 10. So each tick here is kind of an additional power of 10. So number 1 here is 10 cycles, 2 here is 100 cycles, 3 here is 1,000 cycles, 10,000, 100,000, and caps out at 1 million. Okay. And then on the vertical axis here, this describes to you the amount of stress that the material can withstand for that number of cycles. So as the number of cycles increases here, you can see that the amount of stress that we can tolerate those things. Okay. And if you want to see the actual tabular format for this, the actual table that has the exact values is given to you. As you can see here, so once we kind of progress from 10 cycles all the way up to 1 million cycles here, the amount of stress that we can withstand goes down by about 2 orders of magnitude, which is pretty big. Okay. Okay. And so let me just show you kind of really quickly, if you wanted to add your own material, let's call this a new material. Okay. So I'm just going to show you, how you would actually add this, have that information. All right, so if you recall, so it's been a while since we've made our own material, so I think we only did that in activity 2. But remember, the main thing that you have to add to the new material is the type of elasticity that you're going to put in. So the most common one is the isotropic elasticity, and so that's going to have you define the Young's modulus and the Poisson ratio. Okay. So once you define that, then that material at the very least can be used for static analysis. Okay. But if you wanted to add fatigue life behavior, okay, you would have to enter in data from another field over here. From the toolbox here on the left, if you open up this menu here under life, you'll see here that there are various types of fatigue life data that you can put in. So the most comprehensive one that you can put in directly is the SN curve. So if you click and drag SN curve to this material here, right? And you click on this table, right? What you'll see is that there is a way for you to define how much stress the material can withstand for a given number of cycles. Okay? And you would basically enter this in as kind of a tabular form. So let's start with 10 cycles. And let's say that under 10 cycles, this material can withstand, 5E9 pascals. Okay. And if we go up to 100 cycles, let's say that this gets reduced to, I'm just spitballing numbers here. So let's say this gets reduced to 3.5. And then as you add in, additional data points here, that's going to change your graph. So 500 here, 3.25, 9, right? It may be a linear graph, it may not be, but So like I said, information on the SN curve sometimes can be a little bit difficult to find unless you have information on that material itself, the exact material testing. Sometimes you can find that in the literature, sometimes that's you can find it within some material data sheets. But I've in the past I've had difficulty finding this exact information. So just kind of be aware of that. Okay. All right, and there's other ways that you can add in the SN data as well. So you can see that there's linear SN curve, and so for linear SN curve, you just have to define just the starting point and the ending point, and then it'll draw just a linear line too. Okay. And there's also bilinear SN curve where you can define two different slopes. So just like we saw where the I think when we went over nonlinear material properties, we said there was a bilinear plastic deformation curve. Same thing here. So you define kind of two different slopes, and you define where those two regions are, and that'll define your SN. Okay, but for the most part, you're probably just going to be using a built-in material here, like structural steel. If it already has the SN curve, I would just go ahead and use that. You don't have to bother with making the material unless it's absolutely necessary for your. Any questions on this so far? Okay, good. Okay, I'm just going to delete this new material just because we're not going to use it. Okay, so once you are ready, so once you kind of defined, you've uploaded your geometry, you've made sure that your part has the SN curve. Let's go ahead and double click model. And from here on out, everything that we're going to be doing is within. Okay, so here we have our bike crank. We haven't seen this guy in a long time. All right, so first thing I'm going to do, let's simplify this geometry. So let me go ahead and suppress our two strenuous parts here. Let's suppress the pedal, and let's suppress this guy here. Okay, so that we are just working with this one part. Okay. And by default, just for today, we're using structural steel, so you can see the material for this part here is structural steel. But if you are using a different material, just double check, just make sure that you are using the right material for your analysis. Okay, so from here, our fatigue life analysis progresses, very similarly to any FBA analysis here. Okay. The first thing we're going to do is we are going to define our mesh. Okay. So let's make a fairly small mesh here. So let's make sure that we are the quadratic elements, and our element component size here, let's say it could be, let's say it could be 10 millimeters. Let's see how it goes. So let's go ahead and generate our mesh. It's a little bit too big for my liking, so let's cut this down to maybe 5 millimeters. Still a little bit too big. Let's go down to 2 millimeters. Okay, that's pretty good. You can of course tinker with this, and so if you think back to our ANSYS activity, so I think a lot of people did hex equal mesh with this. So feel free to do that. Okay. We need to add our boundary conditions, so let's go ahead and fix support. So let's fix it on this side, just like we did in activity 2. And let's go ahead and add a load. So the load is actually going to be really important. So what ANSYS is going to do is going to alternate your load. And so wherever you put your load, make sure that you're prepared and make sure that you know that that load is going to be alternated and cycle, up to many times. Okay. So let's go ahead and add in a force. Okay. I'm going to add in a force on the pedal. Cover every previous surface. Okay, so actually I'm going to change it up a little bit from activity 2. Remember, for activity 2, we applied our load in this direction. Okay? And that made sense at the time because that was a load that we said was kind of an extreme condition. So we say that maybe our bike crank got caught on something and we're applying this kind of this bending load to our bike. Okay? But a bending load like this is usually not something the bike crank is going to experience over and over and over. And so you have to think about that when you're applying your fatigue life analysis. That load magnitude and your load direction is something that's going to be typical for this structure to experience many times. So it's a little bit of a shift in paradigm in terms of how we do our simulation. Usually what I tell people for when you're running a static simulation, think of the worst case scenario for your simulation. And that should be your load. For fatigue life, you're not looking at a worst case scenario, you're looking at a very typical scenario. Something that this part is going to experience hundreds of thousands of times, millions. Okay. So what I'm going to do instead, right? Something that's more likely to occur on a regular basis for this bike crank, regular setting, is a compressive force. Say compressive, I drew the arrow in the wrong direction. Compressive force. Okay. Right. Or tensile force, that can happen too. Okay. So something that the bike crank is more likely to experience, many times for a regular bike is, a compressive force. So I'm thinking of a situation where someone is riding a bike and maybe they're coasting and they're standing up on their seat, and so they're applying their weight onto the bike crank. So the bike crank is experiencing this compressive. And that can happen, a couple dozen times during a typical ride over the course of a bike's entire life cycle, which is probably happening, tens of thousands, hundreds of thousands. Okay, and so with that in mind, let's go ahead and apply our force in that direction. Okay. So instead of defining it by the vector, let's define it by the components. And let's define our force in the minus x direction. Let's change the pounds here. Let's say I'm talking minus 100 pounds going in that x direction. Okay, so before we do our fatigue analysis, let's do our standard static analysis first. Let's review our total deformation. Let's review our equivalent stress. Okay, let's go ahead and run our simulation here.
That's it?
Yeah.
How much was the force?
100 pounds. Okay. So under that loading here, we can see that we have very modest deformation here. So, for a steel bike crank here, applying only 100 pounds, you can see that our our deformations and our stresses are extremely modest. That makes sense, right? And so for a part like this, 100 pounds is practically nothing. And so it makes sense that our acute results or static results here are very weak. Okay, so now let's do our fatigue analysis. And so to do fatigue analysis, it's quite simple. Okay. So under solution A6, you're going to right click, you're going to insert, and then you're going to come down to the bottom here to fatigue tool. Okay. Now fatigue tool, that's the main way that we're going to, that's the main tool we're going to use to apply fatigue knife analysis to any static analysis that you. Okay, so let's go ahead and click this. Okay. And so as soon as you click the fatigue tool, you're going to see that our setting here is going to change. Okay. You no longer see the part, but the part's not gone, right? When you click on mesh again, you can see the part's still there. But the reason that our display has changed to this is that we have to change certain certain settings about our fatigue analysis. Okay. And so we're going to turn our attention down to the bottom left-hand side, and we're going to set different settings for our fatigue life. Okay, so the first thing that we're going to set here is the type of load. Okay. So you can see the default here is called fully reversed. And so what that means is that, as ANSYS is going to be simulating the fatigue, it's going to fully reverse the direction of all of your modes. Okay. So you can see right now in the default settings here, we have a compressive force of 100 pounds. Okay. Now, if you kept that setting as fully reversed, that means ANSYS is going to simulate what would happen if you were to fully compress the part and fully tense the part with the exact same load magnitudes as well. Okay. And so that's what it means to be fully reversed. So it fully reverses the direction. And every time the direction changes, or every time you make kind of one full cycle, fully compressive, fully tensile, and back to fully compressive, that consists of one loading. Okay, so if we go back to the fatigue tool, so that's what this curve is showing you here. So that shows you the relative magnitudes of the force. Now it's not showing this to you in terms of 100 pounds. It's showing the scaling factor that's going to be applying to your load. Okay, so a scaling factor of 1. So a scaling factor of 1 means that it's going to be applying your loading in the original intended direction with the same magnitude. Okay. And a loading magnitude of -1 means that the load is going to have the same magnitude, but it's going to be in the reverse direction. So that's what this curve here represents. So the load is going to oscillate from fully compressive, fully tensile, fully compressive, fully tensile. Okay. And if you're doing a more complex case, just know that every time that you apply a force or a load, a fully reversible fatigue life analysis means that it's going to switch direction. Sometimes you want that. In this case, that is what we want. We do want a fully reversible loading, right? Because I think for a bike crank, it's just as likely that our bike crank is going to be fully compressed. But if you don't want to reverse the direction of the load, you can change the setting here. Okay. And so another way that you can define the loading history here, or the loading magnitude, is to do what's called zero base. Okay. And so maybe you don't want to fully reverse the direction of the load, but you do want the load to oscillate from fully engaged to zero load. Okay. And so by changing this type here to zero base, you can see here that our curve here again still has a maximum of 1. So the maximum of 1 there is, means that you're applying your loading with the exact same force, magnitude in the exact same direction. But instead of going down to -1, you can see here that the curve bottoms out at 0. Okay, so it's going to oscillate between fully engaged and no force at all. Fully engaged, no force. Fully engaged, no force. Okay. And again, every time the curve's gonna come, it comes back up to 1 here, that there is 1 cycle. Okay, so that's the first thing that you have to choose for your fatigue life analysis. Whether you want a zero-based loading cycle, or if you want a fully reversed loading cycle. Okay. Now, there's other settings you can do here too, and so if you have a more complex loading cycle, you can kind of input it by hand, and so that's how you do history data. Okay. Now, for ratio, you can kind of define, it gives you a little more flexibility on this curve as well. Whether you want to have, the forward cycle to be higher magnitude than the reverse cycle. So that's the way that you do it. Okay. But the most basic way that you can do this is you fully reverse or zero. And if you want to increase these magnitudes here, you can increase the scale factor. So, let's say I change this to 2. Okay. Now this curve is going to oscillate for twice as much load that we applied to twice as much load that we applied to the opposite. I'm going to keep this at 1 for now. Okay. All right. So the other thing that we have to do before we launch it is we have to specify what's called the mean stress theory. Okay. Now the mean stress theory, this describes different approximations of different theories in terms of how the material fails with a certain amount of cycle. You have a couple options here, a few options actually. Okay. This is kind of where I kind of tell you about the limitations of my own knowledge, and so I don't have that strong a background in material science, and so probably like someone like Dr. Sue or someone or Dr. Lee would be able to tell you the intricacies of these different models here and kind of what they mean for fatigue life analysis. Where I'm at, and what I usually do is I just pick the one that's most popular, and I use that one. But just know that there's different options here for different ways of computing the material fatigue scale. So just kind of be aware of it. And, you can kind of do research on it as well. But this is something that I don't have that much experience on, so I'm not correct. So the one I'm going to use here is the Goodman cycle. Or the Goodman theory, just because it has this kind of nice linear drop off from zero loading to ultimate failure. Okay. The other one that I'm familiar with here is the Soderberg theory. Okay. Where the Soderberg theory will tell you that your material is failing once it reaches the yield strength. Okay. So the big difference between Goodman and Soderberg is that Goodman will take your material all the way up to ultimate failure. Whereas Soderberg will only take it to when you get the first signs of yielding, you get the first signs of plastic deformation. And sometimes, depending on your application, you may want one or the other. But for now, I'm just going to just use the Goodman, the Goodman stress. Okay, and you can specify which stress component that you want to use to evaluate failure as well. So the default here is the equivalent stress, the von Mises stress, and you can also do normal stress in a given direction, maximum principal stress. Okay, but I'm just going to stick to von Mises. Okay, any questions on the settings for the fatigue? Okay, good. Okay. All right, so before we launch our analysis here, we do have to specify some outputs here. So actually, you can right-click on fatigue tool, and you can insert different, results that you can show here. Okay. Okay. So one useful thing to show is life, right? So the life result will tell you the raw amount of cycles that ANSYS will estimate that your part can undergo before failure. Okay. So that one's always useful to look at. Another one that's useful to look at is the safety factor. Right? So that's usually something that you want to look at for long-term fatigue analysis. Okay. Let's go ahead and specify the safety factor as well. And so once you've loaded those two results, let's go ahead and click on solve. And you'll be able to see, how many cycles this pipe frame can withstand based on the loading that we discussed. Okay. All right, so by clicking on this life here, we can see that the bike crank can withstand 1 million cycles. Okay. So with the very modest amount of loading that we applied, we can basically say here there's absolutely no danger in this bike crank undergoing fatigue failure. Okay. And you can see that same information under the factor of safety. The factor of safety, you can see we have a factor of safety of 15 across the entire part. Okay. So based on this fatigue life analysis, we can say that this part is probably not in any danger of under a moderate, fatigue, a moderate cycling load. Okay. Now, that's great, and so that's great news for our bike crank, but that result is a little bit boring. So let's increase this loading here so that we can start to see some. Okay, so if you want to increase the magnitude of the loading, let's increase the scaling factor here. So let's increase the scaling factor to 50. Okay. So that's going to increase the magnitude of the loading by 50. Let's see if this reduces our life. Okay, good. Okay, so by reducing our, or by increasing the magnitude of the loading, you can see here that we get much more interesting results for our fatigue life. Okay. The first thing you'll notice here is that different parts of the or different areas of a part are highlighting by different colors. And the colors here will tell you how many cycles that part can undergo given this amount of loading that we're specifying. And so you can see the minimum amount of loading cycles we have here is 78,054 cycles, which is all concentrated in the middle of it. Okay. And that makes sense because the middle of the bike crank here is the thinnest, and so that's where it's most likely probably going to fail if we were to load this with that amount of loading. Okay. Okay. But this is a pretty extreme amount of loading. So this is 5,000 pounds that we're loading, and we're loading, and we are doing the opposite direction of 5,000 pounds over and over and over. Okay, so let's look at the safety factor now. And so you can see our safety factor has changed quite a bit as well. And so we still have the same maximum, right? And so down where the bike crank is fixed, we have a very high safety factor there of 15. But because we are failing at a very low amount of cycles here, our safety factor in the middle of the part here is only 0.3, which is very, very low. And so if this were the results here, we'd probably look to redesign our part, to withstand this amount of load. Okay. All right, and so that's about it. And so that's the additional information that you get from the fatigue tool. So you can go ahead and keep playing with this. And so I did a little bit of overkill here with 50. So let's see what happens with the loading factor of 10. We may get something a bit more reasonable. Okay, so with 10 here, we can see here that our part is still good, right? So our part is still good to survive a million cycles. But our safety factor here is a little bit less. Right? So you can kind of play around with that tool and kind of see how that affects. Any questions on the fatigue tool, fatigue life analysis? Okay, all right, and so that's all I had planned for today. So we have about 20 more minutes of class left. So I know it's a bit early. I just assigned the project on Tuesday. But if you have questions on the project, you want me to look at your CAD file or your project, now's the time. If you have questions on activity 6, feel free to ask here as well. But yeah, that's all I got planned. So thank you guys for coming today. If you guys are heading out, then I hope you guys have a good weekend. Okay. Okay. Yeah. So I did a lot of research into the report. Found a couple other papers. Yeah. So the other papers are really interesting. I think one of them. So I think that'll be a good reference. Try to replicate. Okay. You did. About the mesh, we can talk about it now, we can see. Once you type it out for, it looks like someone has a question here, and then I'll come in.
How complex do you want the artificial?
It doesn't have to be,
Like not a three outside perfect cube, right? But like it is,
Mhm.
or like the midterm project.
probably a little bit closer to the midterm project. So the bike might be a little bit too simple. You're talking about the plan, not this bike. The actual bike. That one might be a little bit too simple. Like I would probably try to add maybe a couple extra parts to that assembly. Yeah, so something kind of in that block. It would help, but I'm not opposed to a single part too. There are some single parts that are quite complex. If you can do the valve project with just the valve part, then that's fine. Yeah. Sure. Yeah. So yeah, fluid heat transfer. Yeah, that is a popular one. Next time we have a free day, I'll do that. I think so. Next week we're going to be doing ANSYS activity 7. So we'll probably focus on just that. So ANSYS activity 7 is on modal vibration analysis, and then probably the week after that we will. Yeah, so people have actually had success doing shell and beam elements. I think someone did actually shell elements for the 4-way valve. They were quite successful with that. So I would definitely try. I do know that ANSYS does typically struggle when you are doing a shell element where the thickness varies. And so that usually happens when you have curved parts. So the thickness will be fairly consistent, kind of in certain parts, but when the valve kind of can merge together with other parts, the thickness can be a little bit thicker. So the shell element might struggle there a little bit, but I would try it. See if you can get a mid surface on it. I think it's definitely worth trying. And if you're having trouble with it, then maybe you can kind of look at it. Okay. But it is possible. It is possible to get a shell for a curved surface, for sure.
Sweet. And then for in class time, would we be able to eventually go over like maybe heat transfer or some of the fluid stuff, just so it could be nice to be applicable in this project?
Yeah, someone else requested fluids and heat transfer. So
Awesome.
yeah, probably not next week. So next week we're going to be focused on activity 7.
Okay.
After that, we'll probably devote that to heat transfer and fluids. Quite a few people have been asking about that.
Awesome. Yeah, sounds good. I'm not sure I'll hold off that long to wait for it to happen, but nice to know that it'll be covered with enough detail to maybe answer some lingering questions.
Yeah. So if you want to get started a bit early on it, you can check out the handouts for it online. So I forget which handouts they were, but I do have the handouts for them posted online already. So you can check them out, and then we'll go over them together in a couple of weeks.
Okay, sounds good. All right. Thank you.
Thanks.
It's good that always get to check it. First. I mean, it's starting result.
Wait, yes. You know what? You need the same eigenvector for both. Yeah, repeated eigenvalues. For example, like if find the first eigenvector, then you use that for the second.
For double words?
Yeah. You have to do
If you want, it's really up to you.
For general solution, you would have to find B.
But if you have those five
Fine. You can use the same ones.
For eigenvectors,
the requirements of the project.
it's usually the same one, but there was an example.
No, but it really depends on the metrics that you find.
That's
It
why I
doesn't
think-
depend on the, if it's
but these
double
all
or something,
are built in.
but if you find something like this.
They might have the peak data.
Yeah, almost.
They have it.
That's the one. Two,
But I tried to.
zero using that.
Yeah.
Said it had
um,
2/3.
Oh.
So
Oh.
if you find something like this is a double.
I would just try, I mean. it
Find
should work
something
with
like
steel,
this.
steel is very well.
The result, you
But
have
for the other
to
one is just.
first-
It didn't much.
and let
Yeah.
x3 be 0. Yeah, spectrum. And then because it depends on which one of you gave 0, because you have 3 variables. You have to give x2 0, find another one. But this doesn't matter with the double roots.
Just for like my general condition, right?
Yeah, because we had some examples with double roots, but Fullerton has the same vector.
It's like,
This is for polynomials. So, last Tuesday, you have to, but not close, but
yeah, the same thing too.
you have to find the different vectors.
Yeah, I asked him to get it before. It's in polar solution, who's been going back to it, but it was.
Yeah,
The same.
I got confused just like an hour ago from that. Oops, something. In my class. This one. It has 2 letters, yeah.
So you can just like,
After seeing the data, it depends on the matrix you find. There's no way. Because x1 is equal to 0. Either way. It's small. So you have to do x1 is 0. But if this wasn't the case, you could give another one 0 exam, then you could another item like to. It's kind of complicated there. I don't know, but I think I will understand why if I see the methods and the methods.
it's saying repeating this.
Yeah, yeah.
I feel like it's in this.
I think you might see it on spring.
2%. 2% we see negative.
Not going.
Yeah.
Solution finding.
So the valve one is probably the first one that comes to
Cold
mind.
spring.
So the valve, you know, you can use structures and fluids on that one.
Initial conditions.
Honestly, probably the most interesting one is probably a combination of thermal and structures. Because heat transfer is gonna affect the material properties of the.
It's complicated.
I think it's gonna be this.
So one project that people have done in the past is a brake rotor. So brake rotor is one that, you know, heats up a lot because it's undergoing friction, you know, as the vehicle is braking. And that changes its material properties a lot as well. So that's maybe something you can look at. I know people have done it for the formula brake rotor before. That's why I've seen it quite a bit. But maybe if you want to find one for like a high performance car or something like that. I think that one might be interesting to do. It might be hard to find a CAD. It might be hard to find a CAD file for like the brake rotor of a Lamborghini. But you know, you can kind of see what you can find
So
online.
it's gonna give us the
Yeah.
calculations.
Sorry, Phil.
May
Alright, yeah, let me know how it goes, and then if you're having trouble finding a part, we can think of something.
Tag solution in sprinkles. So you're gonna give us initial conditions.
Oh, yeah.
Thanks, you too.
1, 2, 1, 0, so you're gonna have to like. Level 1, level 2, it's like this. This value is 1 minus. And if it's come to this, it's gonna take a long, nothing.
Obviously, it's gonna be 0% signable with negative constant. Obviously, he said so. Lifetime.
Now, it's gonna be
This. Two of this.
it's gonna be 2, 1, 2. Something to
I think it's just going to be.
I probably. Box.
Yeah.
I thought that I'm very okay, and the box looks like this.
Okay.
But like. That's like just trying to like suggest like I thought
You can wait until we do activity 7. So activity 7 is a pretty popular.
vibration.
Yeah, so like finding the modal frequencies and resonant frequencies. Yeah, that one might be a good one for this one.
I was thinking that too. I don't know how to implement like the springs and dancers with this.
We'll talk about it next.
Okay.
Yeah.
Yeah, something. E or E. Omega T. So it's C1 constant. And then do I is constant becomes a 1 and B1. So you just convert to C1. You don't do Knowing the I, it's gonna be C1. If this was,
It's like we're like, right?
yeah,
Like, and. So it's how do you write this idea? So like two different concepts.
and but this is the reason we get rid of the C1 and C2, right? Because we already have another constants.
It's- Like choose, if you want to, you don't have to choose, then you can use C heavy, so.
Did you involve Frankfurt? Did you involve Frankfurt?
I would have done 4.22.
Oh.
No, neither.
Didn't you take that last semester? Was Anthony?
We did lessons. Maybe we did six, but- Because he's got his definition of this, but I don't know if they're going to say. You do it, at least it was amazing.
I think it's one. I'm fully online. But because yeah, that's yeah.
But no, it's like a hard, so that's what's what I want. Two other classes are pretty. So.
I'm not forgetting. No, we're at 597. And 8 or 7. I don't know which one. A thesis class. That also makes sense, like I said. Also makes sense.